If you want to improve your problem solving skills on data structures and algorithm related problems, then there are already a lot of resources out there on the internet. However, one shortcoming of all of these resources is that they are highly topic specific, meaning the practice problems that you do from these resources, they already contain the spoiler tag that this problem can be solved via DP or via greedy or via two pointer or via sliding windows and so on. So in this manner, you don't really improve your thinking skills. And when you are in an actual interview or a contest setting and you encounter a completely new problem, you freeze and you are not able to map it out to a known data structures or and algorithms. So instead of reinventing the wheel, I'm start I'm trying to start a new video series on my YouTube channel where I will focus on the ideas instead of the code implementation details or the optimization. I'll pick any random problem and I'll walk you through the process of how I think about it and how I lead my thoughts to the correct direction so that it can be simplified down to a known data structures or algorithm problems. So that is why we'll just be focusing on the ideas instead of the code. The code is completely optional. If you don't want to implement any of the problems that I discuss in this video series, that is completely fine. You will still gain the maximum benefits from this video series. And then I also want to focus on the correctness instead of the time complexity of these problems. But that doesn't mean that we'll simply implement an exponential solution and move on. No, we'll will not focus on the time complexity much, but we'll still do the correctness part, but in such a way that the solution that we have come up with can be improved upon later with some known data structures and algorithms. And that is why when the time comes for improving the time complexity, instead of discussing those in details, I'll just give you references on how you can do that by yourself. So this series will mostly be about brainstorming. So let me know how you feel about this series, and if you have any feedback or suggestions, do let me know in the comment section so that I can make the modifications as we go along. So in this series, we'll cover problems from Leetcode, Codeforces at Coder. But for you, it should not matter where the problem came from, right? Because in an interview or a contest setting, a problem is a problem, right? Doesn't matter the source. So this is the first episode of the series, and in this problem you are given an array and you are allowed to do multiple operations on this array, and in one operation you pick an element, say AI, and you pluck it from here and then you move it towards the end of the array, and after you delete this element from here, this will shift to the left and this element will move to the end, and then you also have to increment this element by 1, so that is why AI will transition to AI plus 1, and you are allowed to do any number of operations on this array, and your goal is to figure out the lexicographically smallest array that you can get after doing any number of operations. So a benefit of solving this problem is that the next time you encounter a problem that talks about lexicographical ordering of an array, you'll have some insights on how to start the thinking process. So you'll see later in the video what this implies, and what are the invariants or some key concepts that you can use in any problem that involves lexicographical ordering. So take a minute to pause this video, and you can already see the entire problem statement on the screen, and try to come up with a solution no matter the time complexity, but it has to be correct, and try to convince yourself on why it is correct, right? You don't have an online judge available with you, as you would not have one in an interview, but try to come up with any approach, and even if you're not able to come up with an approach, see how far your thought process leads you to before you go on to the next slide, which contains a lot of spoilers. So one important thing about lexicographical ordering is that the first element or the first mismatch matters more than the elements that come after it. That is, if you have an array where the second entry is infinity and you have another array where all the entries are small, but even then the first array will be lexicographically smaller, because it doesn't matter what comes after 1, because if the first element itself is smaller than the first element of this array, then this array already won. So in lexicographical order, now you can see in lexicographical order, your first key concept is that the first element has to be minimized no matter what, even if it comes at the expense of these other elements. Even if you have to make all the elements infinity to achieve the lowest over here, you have to do it. So then that should lead us to the second spoiler, that is, if you have this array and you already know that in one operation you can increase the element by 1, right? So what are the candidates for the first element that can be the smallest one? Because if you apply the operation even once, you will end up increasing the value of an element by 1. So your goal should be to pick up the minimum element. So this green element is the minimum valued element, and you have to pick up this minimum element and then you have to somehow preserve it. This minimum element should not participate in any of the operations, otherwise its value will increase. And we already know that the first element has to be preserved or minimized no matter what. So this leads to our first conclusion, that the minimum element of the array should remain untouched. You should not do any operations on it, right? This should remain as it is. It should not move from its place. So if it does not move from its place, it means that all the elements that are to the left of it, they have to migrate to the right hand side, correct? Because there is no other way that this element can become the first element. So if you look at this spoiler, then you can see that since since this will be the final since this will be the first element of the final array, then all these elements will migrate to the right, and every time an element migrates to the right, it gets incremented by 1. So we know that this entire LHS will be incremented by 1 and they will migrate to the right hand side. But in which order will they migrate? Like, do they have to migrate immediately or eventually? And if so, what should their ordering be? Like, should their ordering remain the same, or should this element migrate first, or should this element migrate first, and so on? So to think about that, let's look at an example. So if you have this array, and this is the minimum element you see over here, and then you can see that everyone has to migrate to the right hand side, right? And then given the choice, would you like to migrate 10 first or 2 first? So you can already see that if you migrate 10 first, then 10 will be over here and then 2 will be over here. But then we already saw that the previous elements has to be minimized no matter what. Then you are already making suboptimal choices, because if you had migrated 2 first and then you had migrated 10, then a smaller element is to the left of a bigger element, and this sequence is lexicographically smaller. So then we come to another conclusion, that the migration will happen after incrementing all this values by 1, of course, and the migration will happen in a sorted order. So if you look at this, now the migration will happen in a sorted order, sure, but there is no rule saying that you have to do the migration immediately, right? You will have to do that eventually, but no matter when you do, 2 will always be the first element to migrate, then 3 will be the first element to go from the left hand side to the right hand side, then 5, and so on. So we have our next conclusion, that the migration should happen in this sorted order, but it might not necessarily be in a contiguous order. Like they can go at different times, but whenever the time comes, 2 will go first, then 3 will go, then 5, and then so on, right? Now, yeah, So now let's say at whatever time the migration happens, what about the second minimum element, right? We have found out the first element that will be part of the final array, the lexicographically smallest array. What about the second minimum element? So for the second element, the second element also has to be the minimum element from the remaining ones. We should not be touching the remaining elements, otherwise we would end up increasing it by 1. So it will either be the minimum element from this right hand side, or it will be the minimum element from this left hand side. And keep in mind that this left hand side has already been incremented by 1 for each entries, because we know that eventually the migration will happen. So the second minima, it can either be located on this section or on this section. Now let's explore the first case. What if the second minima, and by second minima I mean comparing all of these values to all of these values incremented by 1. So suppose that the second minima is present over here. What can you conclude? If the second minima is present over here, should you do the migration right now or should you delay it? So if you delay the migration, that means if you do any migration on the right hand side, like these elements migrate amongst themselves, like this goes here and so on, then eventually this element has to migrate, and all the elements that are in between, they also have to move to the right of it, right? So like there cannot be any gap between this green box and the second element that is migrating to the right hand side. So this means that if the second minima is on the left hand side, then you have to do the migration immediately, and then you have to clear all the boxes in between as well. So you can see that if the second minima is on the left hand side, like this is the minima and this is the second minima, if it is on the left hand side, you immediately move this blue box to the end. So this will be the blue box, and after moving the blue box, you know that you cannot touch the green box, and you know that these elements will already migrate, right? They will already transition to the right hand side. You already incremented these values by 1, and then you can also conclude that this middle section, right, they also has to migrate to the right hand side of this blue box that will eventually land over here. So now we know that whenever a set of elements have to migrate, they have to migrate in a sorted order. So if this element is migrating over here, then these entries are now in a sorted order, and these entries are now in a sorted order, and all of them needs to go to the right hand side. So there is only one way you can do that, which is by picking the minimum element and then placing it to the right, then picking up the second remaining minimum element and then picking up to the right. So that's why if the second minima is on the left hand side, then the entire process ends with incrementing this right block and then sorting and then doing the migrations one by one. So now pause this video and think about why this case is correct for the minima on the left hand side before moving to the minima on the right hand side. So now let's handle the case when the minima is on the right hand side. So if this minima is on the right hand side, let's see what will happen. So if this is the minimum element and the second minima is on the right hand side, then you can see that you cannot touch this blue box anymore, right? This means that all of these elements also have to migrate to the right eventually, not immediately but eventually. And we said the same thing about this one, right? So this means that you increment all of these values by 1, you increment all of these values by 1, and you club them together, because now they will all migrate in a sorted order on the right hand side. And then you repeat this process, because once you have found this blue box from this green box, which is the second minima, this is the second minima, then this can act as the green box, and then it will look for the minima on the right hand side. But if the minima for this blue box, if the next minima for this blue box occurs on the left hand side, it means the entire process ends, right? Because you have to immediately migrate this element over here and then do the migration of the remaining entries on the left hand side. Otherwise you simply continue the process. So you see that if the minima is on the right hand side, then you have already done LHS plus 1. Now you will do middle plus 1, and these will go in any order, and the best order is the sorted order. So you go in the sorted order and then you recurse the algorithm that we just discussed. So that's why we have seen that if the next minima is on the left hand side, then the problem becomes trivial. But if the next minima is on the right hand side, then the problem is non-trivial. But we have already come up with the strategy for that. So now all we need is a data structure to uh, like quickly increment all of these values by one and then do the sorting, etc. But if you understand the solution so far, like if you understand the overall idea, then even if you don't watch the remainder of the video, you would have like gotten the benefits out of it, because the goal was to convince you that this strategy would work. Right now, how to implement this strategy uh, optimally, that is up to you. So to do that, one simple strategy that you could do is, every time you are interested in the minima of the right hand side, basically the suffix minima, and the prefix minima, but prefix minima you are adding some delta every time, but then you are also keeping the prefix in a sorted order, right? Because we have seen that if these elements need to migrate to the end, then they should always go in a sorted order. So that is why you can use a suffix minima for tracking the right hand side minima, and then you can use a set which has a log n complexity per query to maintain things on the left hand side. So that's why. So now you can see that this problem was actually a two-pointer problem. Why? Because this blue box, right, this will keep on moving to the right. You start with the minima, second minima is here, third minima is here, fourth minima is here, fifth minima is here, and so on. So now, if this problem, if you knew that this tag was two-pointer, then you would have tried to enforce two-pointer on it. But since this was a completely new problem, then we ended up accidentally stumbling on that two-pointer strategy, and you can say that in a way that it is also a greedy strategy, right? But all of this is in retrospect, right? When you start thinking about a problem, it's not immediately clear that it has to be a two-pointer problem or not. So that's why you can use suffix minima and the such data structure to solve this problem in nlogin. So now what can you take from this video? So the learning is that every time you encounter a problem that deals with lexicographical ordering of an array, you have to remember that you have to optimize for the first element, even if it is at the expense of the other elements. Then once you have optimized for the first element, you have to optimize for the second element, even if it is at the expense of all the other elements. Don't try to distribute things amongst all the elements. Everything should go to the first element. All the efforts should go in making sure that the first element gets what it needs, then to the second element, and then so on. So we'll quickly look at the implementation. So first we want to compute the suffix minima. So you can simply do that by iterating the array from right to left, and then maintaining the suffix minima. This is a very standard technique, but here you also need to jump from one index to another. So instead of just maintaining the suffix minima, I am also maintaining the indices of it. So nothing new over here. And then what you do is you locate the minimum of the entire array, which will be suffix 0, because this suffix minima of this entire array is the minimum value. So suppose it is this green box over here, and then you store all of these elements in a multiset, because they will go in a sorted order for sure, right? So you insert all of them in a multiset, and you know that this element is never moving out of its place. So all of these will have to migrate to the right hand side. So that's why you increment all of them by one, right? And then what you do is you try to find the blue box, which is the second minima. And how do you find the second minima? You either look at the minimum element on the left hand side, right? But remember to look for the minimum element with the values incremented by 1. So that's why you either look on the minimum value of the set that you have created, that multi-set that you have created, or the minimum value on the right hand side, which is simply a of suffix r plus 1. And then if the left hand side minima is the smaller one, then it means that you have to immediately move it back, like you have to immediately attach a blue box over here, and then for the remaining elements you have to do the migration in a sorted order one by one, right? So if the LHS minima is smaller, you simply terminate the entire process by taking the middle box or the right hand side box into your set by increasing them by one and then terminating the process. But if the right hand side minima, like if the blue box is on the right hand side, like the second minima is on the right hand side, then you know that this middle section, right, this middle section will migrate on the right hand side, and so you increment all of these values by one. And when, how, in what order will they migrate? So these elements are waiting to migrate in a sorted order, and these elements are also waiting to migrate in a sorted order. And since we do not have any restrictions on when to migrate and like which element to migrate first, they can be clubbed together, and then we can migrate this entire thing together in a sorted order. So that's why you simply push them in a remaining set and then you carry on forward. So yeah, this was the problem. So take a minute to like go over this problem statement again and think about why this strategy works, right? Implementing it is not a big deal, but convincing yourself of like how these greedy approaches and lexicographical ordering etc work, that is the most important part. Now in the comment section, do let me know, like if you encountered this problem on Leetcode, would it be a Leetcode easy, medium, or a hard problem? Or from a Codeforces perspective, what would you guess the rating of this problem to be? And if you found this problem in a Codeforces contest division 2, would this be in position A, B, C, D, E, or F? Do let me know in the comment section. As well as if you have any feedback or suggestion for me for this, for continuing this playlist, do let me know and I'll make sure to incorporate your suggestions. Thank you.